Assalamu alaikum everyone. So today I would like to show you on ANSYS that how can you validate or find out the drag of a bare hull by the means of ANSYS Workbench 2024 R1. So first uh, I took a DTMB 5415 hull, which is a model. Uh, its specification is 5. Its LPP, length between perpendiculars, is 5.72 meters and its draft is 0.248. So first what we will do, we will change the segment and go to front and drag a line here, and suppose we will do the offset and type 0.248, which is the drag. Now what we will do, we will extend this line up to the this segment. Then what we will do, we'll go to perspective. Our goal is to set, so our goal is to set the draft at the reference point and the coordinate of 0.000. So what we will do now, uh, we will draw a line which is touching the point of the hull, and we will extend this up to. Now we shall take the hull, this line and the reference point, and we will just press move and just simply write 0 comma 0 comma 0. As a result, you will see that the hull is now shifted at the point of 0 comma 0 comma 0. In order to import this hull, so first we are setting the reference point. The only reason is that when we are taking this to ANSYS, we must have the reference point with respect to which we will set our domain, as per which we will find out the drag force. I hope the OBS studio is running okay. Good. So as I said, that draft at transom 0 comma 0 comma 0, that's the coordinate for XYZ. So setting the transom at draft at origin, now I will ensure that this hull does not contain any non-manifold edges or any naked edges, because if it contains any non-manifold or naked edges, the ANSYS will consider this whole hull as a surface but not as a pure solid body. So I will just join all the segments, and you can also use Boolean union. Select the curve and paste. Then for double ensures, you can you can say make solid, oh sorry, create solid, and just press enter. Now if you want to see that if there is any non-manifold or naked edges, we will just simply type the command show edges, and you can see if I select all edges, the pink line is shows it all and naked edges, and you can see here there is no naked edges and non-manifold edges. So um, it we can easily just transfer this to ANSYS Workbench. But first, the most important factor is to save this file as, suppose we are saving it in downloads, and this is the most important. We will save the file as step file. Step. Most of the time in most of the videos it is shown that IGS file, but in ANSYS Workbench 2024, if you're running in the student version or in any version, IGS file, importing from IGS file makes sometimes ANSYS find the surface as surface. But if there is no, even if there is no non-manifold or naked edges. But if we just transfer this STP file, then we can be 100% assured that it will consider it as solid edge. Now just click STEP and save. Here there are many AP203, AP214. We will just go with the most latest version of STP, AP242, and we will just create OK. Our work here is done. Now what we will do, we will just open ANSYS workbench. We will just drag here fluent, and in geometry we will basically work in new design modular geometry. It will take some time to open. I hope the OBS studio is working fine. Yes. Now we will just export the file, import the file that we just saved, this PC. If we just open this and create generate, then what we will see, this is a solid body, then this is a solid hull in ANSYS design modeler. Now what we will do, we will create our domain for which our fluid will give us the drag force if we just steady state fluid. Now what we will do, we will go look at, then we will go to sketch, and then we will go to build a rectangle. You see why I chose the reference point at this point, because using this I can I'm setting this as the reference point and selecting the top forward of the domain and behind of the domain, and can create the domain in the most accurate way possible. Now I can take dimensions, now let us drag the dimensions here as, what can we say, 20. The front dimension can be 11.5, the back dimension can be 4. Then if we press generate, I hope, yeah, generate. Now what we need to do, we need to offset this. Again we will just go modify, draw, we'll just go to modeling, and we will just go to the we'll just go to create flexible body pattern. We will just go to extrude, and in extrude we will just select this and say OK. And if we just extend this part, we will just see add material is here, add frozen. In the direction I am wanting both ways symmetric, and I'm wanting that the box is at least 4 meter. Okay, now if we press generate, I hope it is generated. Considering the capacity of the configuration of a system, we will just need to next what we will do, we will look at this segment, or just we will stick with this segment, and we will just take this plane, this plane, and we will create a rectangle again as a body of influence. You can give this segment length any way possible. This is the most critical zone, because in the hull there will be both air water interaction. So keeping body of influence here is a very vital thing. So L1, let us keep this 0.5, and L2, let us keep this 0.5 also. uh, this is the most crucial place whether in between the draft there will be air water interaction. L3 can be 21, this can be 14, or in order to make this symmetries, no, yeah, I guess 12.5 would be a better shot. Then we will just then we will again press extrude and select the sketch here and apply. Then we will add material, add frozen. You see, we are not giving here asymmetric because we only need the body of influence in this one way. So if we add frozen, and suppose I just want to keep this like this and hit the press generate, now our domain is created. Now what we will do, we will just remove the hull from the domain and just use the domain with the sculpture of the hull in order to find the resistance. So what we will do, we will just use the boolean. So if your hull and the other segments are not all solids, then in order to do the boolean you may face problems. So we will just select subtract. Then our target body is this one. Then we will press Ctrl and select the body of influence and apply the body of influence and the domain together. Then we will select the tool body, the the body we want to subtract from the domain. Then hit apply. Then just pray to God and say Bismillah and generate. You will see that in the domain I have the sculpture of the hull. See, it's very sharp, the sharp edges of the bow. Okay, now I will just give a cross and I will just go into the mesh. It will take some time. What we can do, now what we will do, our prime factor is, the first thing what we can do is to remove the connections from here. We'll just get rid of the contact, or the children contact. Then in size, mesh is the most crucial part. We will just give, we will just see the statistics. There is no statistics here. So first what we will do, we will just work with the body of influence. We will just here insert add sizing. Now let us first do the naming of the inlet and outlet. That's the most crucial part. We'll just select here and create named section. We'll just say inlet. Then the next segment we select and create, this is outlet. This is the most important part, and we press Ctrl and select the 3 segment and create the name section as symmetry. And I'm declaring this bottom segment as the wall. And I'm also declaring now, in order for me to select the hull, I have to go in a very sensitive manner in which I have to box select, and yeah, then my hull will be selected. Here I can press say declare this is hull. Now we are done with the naming. Here you can see the consecutive naming part. Then what we can do, we can add insert sizing, and we can apply, select this, and we can shift to single select. In the geometry segment we can pick the whole domain, and here in element sizing we can toggle down and select body of influence. Here we can select this as body of influence, and let us set that first of all it is calibrated in meter. So in order for us to work, we have to calibrate it in uh, millimeter. So in order to calibrate in millimeter, the body of influence is 40 millimeter. So 40 millimeter equals to 0.04 meter. Let us set the growth. Let us just keep the growth rate as the default, and we press generate mesh. As per the configuration of the RAM in your system, you will be able to see the generation, the speed of the mesh will fluctuate in that manner as per the generation of, as per the configuration of the desktop you're working with. If you press double click, you can see the meshing. Considering the project you're working with, the, the element size can vary, and depending on the element size or the input of the element size, the mesh can fail and be successful at the same time. So it's a very sensitive issue. You must always consider giving which element proximity curvature, curvature mean size, and curvature angle the mesh is being successful. We should go through trial and error. You may face multiple times mesh failure. That's okay. It's just some bad elements. You need to filter those, and inshallah your mesh will be successful. As you can see, the meshing is complete. If we press mesh, you can see the intensity of the mesh around the hull and the body of influence. See the curvature. Okay, now mm, what we will do, we will just remesh more finely into the hull. So we'll just box select the hull, and we will just apply, and we will give the body of hull 20, so 0.02, and let's give this 12 degree, and I hope, and let's keep the rest of the element size as default, and press generate and see if the meshing is successful or not. So you can see the mesh is more refined now, as I created double mesh in the body of hull, and now this is the main global mesh. Here the element size is given 1.7402, but I don't want the default size to be this much large. Suppose I want the default size to be 100 millimeter. So just give 0.1. And let's give this 12 degree. And here the most important part is the smoothing must be high. If I consider the inflation layer, you can calculate the inflation layer from anywhere where the inflation layer is y plus value. I have calculated mine. Let's just program controlled inflation. Let this inflation and none, and let us consider the first layer height is 0.0012503. You can calculate inflation layer from any website if you want. Like if I just calculate here inflation layer calculation layer ANSYS, then you can inflation layer calculations. Then you can see that you can calculate here, you can calculate here, you can calculate here, saves you online. Here you need free stream velocity, the velocity that will be integrated into the flow, density, dynamic velocity, boundary layer height, and the desired y plus value will be. If you don't get the first layer, you can also set this to program controlled, and you can see this smooth transition. Then you don't need to be aspect ratio, let us consider 0.77, and you see the already existing nodes and element numbers is this. I'm just taking some of the elements for global mesh in order for the perfect mesh quality and smoother convergence of the simulation. If I press generate, then see what happens if my element input is correct. Or so after default, we can see now we can just leave mesh. Our mesh was successful. Although all our works in the mesh is here is complete. Now we need to update the mesh so that we can proceed ourselves to the simulation part. Here you can also show the progress. Now we will just move to the setup part. Here I will use double precision and the maximum number of cores that I have. 6. I have 6 cores. Now it will start the fluent version of the simulation part. It will take some time to load the domain into the simulation part. I'm using ANSYS 2024R1 student version. Uh, so the after loading, you can see this, that the blue part is inlet and the red part is outlet, and you can see the hull. What we will do next, we will select on gravity, press 9.81. Since here Z is showing in the upper part, the gravity will act in the lower part in the negative Z direction. Next thing what we will do is make you can see that if we see the display here and edges, and if we show display, it will show the meshes. Now if we just select only the hull, we want to see only the hull, you can see that this is the hull. Now what we will do, we'll just go to previous part, select and create polyhedral mesh, because these are tetrahedral mesh, triangular. We will just create we will just convert these meshes to polyhedral mesh. It will decrease our simulation time and increase the possibility of the convergence of the result in a more probable and swift manner. Now after the all the meshes are transferred to polyhedral mesh, then we will see the model. Here in multiphase, we'll just click OK, and we will select volume of fluid, open channel flow, implicit body force, and we can increase the current number to 0.3 for faster simulation and convergence result. Then select this interference modeling to sharpen dispersed. I hope, and in interface we will just select this zonal discretization. Then I think most of the things are corrected. Then we will just apply, and hence CD time settings are adjusted. Then we will just go to viscous SST K omega modulus, curvature correction, production, kettle launder. Then we will select an OK. In the materials, we will just use here only air is. We just select fluent database. From user defined database, we will just from fluent database, we'll just go to the end and select water liquid. It has all the properties are given here. You just copy here water liquid will be, and then we will say close. Then we will just say close, but the most important thing, we just again need to go to multiphase, and in the draft line there is a air water interactions. We just have to select the phases. Here phase 1 is air, that's correct. Phase 2 is air, that's not correct. Here phase 2 would be water liquid. Then we will just click apply and then close. So we have separated the draft line in solid. In boundary conditions, in inlet, we select, double click on the boundary condition. Here the hull is good. The inlet is velocity inlet. We'll just select this as pressure inlet, and here if we create intensity and length scale, Suppose that let us consider the turbulent intensity as 1% and turbulent length as 0.04, and in multi-phase we will open channel flow, let the velocity be 0.2976, and the bottom left will be the draft or the bottom of the domain, which we will consider as -4. Yeah, then we will just apply inlet. After settings, after checking all that carefully, we'll just close this and go to interior solid outlet. Here we'll just consider static pressure. The intensity and velocity inlet will be same as that as before. In multiphase we will go open chain flow and just give the bottom of the domain, which is -4, and create apply and select close. Now the next thing what we can do is go to reference values, select compute from inlet, and change this to the original density, which is 998.2. The length of my ship is 5.72 meter. The temperature and everything is seems fine. Here you don't need to add solid, you just have to add the blank. Next we will move to the solution. Here the method, in the method coupled least square cell base presto second order upwind. In controls, the zero relaxation factor, for our convergence criteria we can just tweak this. For mine, after doing multiple iterations, I've came to these factors of 0.55. The turbulent kinetic intensity is 0.5, it's 0.4, and the turbulent viscosity is 0.4. No changes were made in the wall shear stress or any other way. In monitor, if we click report definition, if we click on the monitors, then we can, if we select report plots and if we go to new plots, then if we go to the new, we will see that force. Here you can see there's both drag, lift, moment and force. We will just select with go with drag for now. Write this drag and select the, I'm not trying to consider the drag coefficient, instead I'm trying to calculate the drag force of the half hull, obviously. Then I will just click on hull, print to console and select OK. So the drag force upon the hull will be calculated. OK, close. Now you can see there is a drag plot report. These are the convergence conditions, and in initialization part I always go with hybrid initialization. That the reason is that you can also go with standard initialization, nothing matter with that, but in hybrid initialization the benefit is that the tweakings or the corrections that need to be made in k and omega are corrected by the hybrid initialization. We have to select it from inlet, and open channel initialization we have to make flat. Now we shall initialize. This is the most important factor of initialization. After we place initialization, there will be primary iterations would be done. Now after this convergence, hybrid convergence, we will just go from graphs and select the contours. and we will select phases. Phase 2, and now we will select every one to go for second display. So the partition between so the partition in draft of that of, you can see the partition of interaction of air water here. Before, above the draft this is air, and below the draft this is water. Now if you go to run calculations, double click on run calculations, is a time scale factor, and the time scale factor, if I choose 0.5, and the number of iteration, if I give 1500, then if I press calculate, then the simulations will start to run. Convergence dragged result. So these are the scaled residuals. As the number of iterations increases, drag and scale residue will create graph rhythmically and set a value for convergence. This was the video. Hope you like it and hope it helps you somehow. If you find it helpful, do subscribe and like my video, and suggest those who are in need for the projects or thesis for ANSYS Fluent. And if you have any question, do comment or ask me in the email. Thank you.